We'll now look at how SRAM handles nonlinear static analysis. So SRAM's nonlinear static analysis uses a Newton-Raphson method to iteratively solve structures where linear analysis wouldn't be sufficient. It includes p-delta effects. In fact, you can think of the p-delta effect or the p-delta analysis as being an approximation to nonlinear analysis. Basically, the load vectors are broken into increments and they're applied incrementally. And it will provide more accurate analysis results versus its counterparts like linear and p-delta static analysis. It also allows for nonlinear elements, which we'll look at in later videos, and the option to consider not only nonlinear geometry behavior, like large displacement analysis and p-delta effects that we already talked about, but you can also define nonlinear material behavior using link elements. Now we're only going to just scratch the surface of nonlinear analysis. We actually have a training course dedicated to nonlinear and p-delta analysis, the F203 online training course, which you're welcome to attend after you've attended this training. Now when running a nonlinear analysis, again, we need to choose the number of increments or the number of pieces that the load is going to be broken into. And then each increment is going to be solved iteratively until it's within a tolerance. And this is a numerical method, so it's accurate, but it's not entirely exact. And just to explain that, within the context of a simple example, here we've got a fixed base column. And let's say we're applying a load here. We're going to say that this is a 10 kilonewton load, and we're going to break this into 10 increments. So that's 10 kilonewtons divided by 10 increments, so each increment is 1 kilonewton. So we'll start by applying an incremental load of 1 kilonewton. Then we're going to do an iteration until we find a solution. So we're going to solve. We're going to update the geometry matrix, which is something that we don't do in a p-delta analysis. Then we're going to update the stiffness matrix. And we're going to check that the tolerance is within our user-specified guidelines. If it's not, we're going to go back to the previous step. And if it is within our tolerance, then we can go to the next step, which is step number 3, where we report the unbalanced force, and we go back and apply the second incremental load. And we keep doing this process until we've gone through all our load increments. Now I mentioned unbalanced force here in step number 3. The unbalanced force here is basically, you can think that the internal element load vector, it's got applied loads, and we can compare this to the magnitude of the applied loads. And we can actually see this in the solution trail. So if it's a large number, this might be of concern. We might want to increase the number of load increments that we have. However, in most situations that we'll encounter, it shouldn't be an issue, but it's always good just to be aware of what's going on. And more details on this are available in SRAM's help system. We also have iterations. As you can see, this is an iterative solution. So we have the concept in SRAM of defining the max number of iterations. And basically, the iterations stop when the analysis is converged based on our user-specified tolerances. Now, this max number of iterations is only a cap. However, if we do run into problems with the analysis not solving within the required amount of iterations, or the maximum amount of iterations, we would recommend actually, before increasing the number of iterations, increasing the number of load increments. Breaking those load vectors into smaller increments is usually a more appropriate response to that. So we're going to look at an example now where we have a column. And if I just look at the properties of this column here, we can see that it's fully fixed about its base. So I have a fully fixed support. If I render this section here, we can see that it's a Y-flange section. You can see the orientation of the flanges and the webs. And I also have dimensions here, which I can display in the status bar. It's 5 meters tall, and I have a joint at mid-span as well. In addition to this, I've gone to the settings menu and then default constraints. And you can see here that I'm actually constraining the model in the Y translation direction. So every single joint in this model is prevented from moving in the Y translation direction. So there's not really going to be any out of plane action. Under the loads window here, I can see that I have a few different load cases. I have a lateral load case, and I'm just going to display the magnitude here, which has 10 kilonewtons of lateral load at the top. I have a unit vertical load and a 1500 kilonewton vertical load. And that's putting it in compression, the column. If I go to edit, load combinations, I also have one load combination set up as well. So I'm calling this P delta, just kind of memory cue name here. And this just includes my lateral and 1500 kilonewton compression loads. Now we're going to run through the different types of analysis we've looked at and compare the results. So I'll go ahead right now and run a linear static analysis first. So let's go linear static. I'll run it for just my load combination. Press OK to run. And you can see that we're getting a clean solution. Again, I'm just analyzing my load combination. And for those of you that are following along, you may notice here that if you've selected to view a load cases, it's going to say not solved, which is what we should expect since we told it just to analyze our load combinations. So I have to click on the load combination view here, and now I can see this result. And I'm going to look at my deflection. I can see that I have 23.5 millimeters of displacement. And my moment diagram here, you can see that it maxes out at a moment of 50 kilonewton meters. Now let's consider doing a P delta static analysis, which we've already investigated in the last few videos, but I'm going to go with a P delta static. Again, this is going to update the stress stiffness matrix, and it's going to run another linear static analysis on top of that. So with the P delta static analysis, again, we get a clean solution. I'm going to investigate the same results. So looking at the deflection tool here, I actually get significantly more deflection than what I had before. The linear static analysis isn't considering the P delta effects that were occurring due to that deflection from the lateral load and the large P, which is 1500 kilonewtons in compression. So we're getting a much different displacement. We got 23.5 millimeters before. And from my moments, you can also see that this has increased a lot as well. So I'm getting about 288 kilonewton meters of moment now in this situation, whereas before I was only getting 50 kilonewton meters. So the P delta effects are certainly significant in this case. Now let's go ahead and run a nonlinear static analysis. And if I go to choose that option, nonlinear static, you can see that I have various convergent criteria here. We have the option between absolute and relative, and I would say that unless you're absolutely sure what your convergence criteria should be, use relative. It's not just a play on words, it's, I would say, helpful advice. We can also choose our convergence parameter, so this is the number of load increments that we want to enter, basically the number of load factor subdivisions that we're going to make. And I'm just going to start with 1. This is the max number of iterations, and we have a few other values that are relevant as well, like the tolerances and so on. So this is a tolerance that we're going to solve within. So I'm just doing one load increment, meaning I'm actually not breaking down my load vector at all. But if I run the analysis, we'll see what happens. We can see here during the nonlinear static analysis, first of all, we get this little window next to it that says the number of iterations it's gone through. And it's also reporting an unbalanced force, which we can see is very small. So it's gone through just a few iterations, and an unbalanced force is reported here. A very small unbalanced force, meaning that the error within this analysis is extremely small. We can click any key to continue. And now I'll look at the deflection. You can see I'm getting 158.7 millimeters, just like I got in the P delta analysis. And if I look at my moment diagram, 288 kilonewton meters. So what do we notice? Well, we notice that the results in this case are actually the same as the P delta analysis, even though we're running a different type of analysis. So why is that? Well, you can kind of think of a single increment nonlinear analysis as the same as a P delta analysis. P delta analysis will only be able to do one load increment essentially. There are a few other differences here and there, but that's the main gist of it. We don't get the advantage when we just use one load increment of updating the geometry matrix as we go through this analysis, which can actually have a big effect because the nonlinear analysis can consider the change in geometry as we add more and more loads, whereas the P delta static analysis doesn't do that. It just looks at the stress stiffness matrix. So why don't we try this with a few other parameters changed here. So I'm going to go run another nonlinear static analysis, but rather than using one static load increment, I'm going to go with 5. And I'll click OK. And if we look at this analysis here, we can see that it's broken the analysis into 5 different load increments, and it's reporting the unbalanced force and the number of iterations required to solve each one of these increments. We get a clean solution. And now if I look at the results, I can see that I'm getting 151 millimeters of displacement this time versus 158 before. And I'm getting 276 kilonewton meters of moment. So it's dropped a little bit. We'll increase this once more. I'm going to go with, let's say, 50. This might be more than we would need, but I just want to see the effects that this has. And you can see here again, it's ran through the analysis of all 50 load increments and it's still reporting all the unbalanced forces and everything. And once I'm done, I can look at the results. 148 millimeters more or less of displacement and 272 kilonewton meters of moment. So this leads to the question, how many load increments is enough? If I were to then go up to 500 load increments, am I going to notice a major change in results? Well, the reality is that the more load increments we use, the more accurate our analysis results will be. But at a certain point, they're going to converge. And it's up to us to decide when that point is. If you have the time, I certainly recommend going through different numbers of load increments to see if it's going to converge at whatever value you predict it to be. Through experience, you're going to get more and more efficient at this process as well. So you may have the ability to actually know ahead of time approximately how many load increments will work. But we recommend reviewing the results, the moments, the deflections, the shears, and so on, until you notice that a major increase in the number of load increments, which increases the analysis time and so on, yields very small changes in the actual accuracy. At that point, you can say that it's probably not really worth the extra analysis time and model size to get that much improvement in the accuracy. But that choice will vary depending on the engineer.